Okay, good afternoon, everybody. I'm Luca Ciabatta from the Research Institute for Geohydrological Protection of the National Research Council of Italy. And I'm here to show you a new rainfall product developed within H SAF based on soil moisture observations. In this presentation, I will first of all explain why we can use soil moisture for estimating rainfall. Then I will explain the SSM-derived algorithm, the algorithm used for obtaining rainfall through soil moisture observation. And I will also show you the new product we are developing within H SAF. After that, I will show you some applications related to the use of SSM-derived derived products for hydrological purposes. In this graph, you can see the rainfall amounts recorded by 6 rain gauges in a small area. And here you can see that different rain gauges recorded different rainfall amounts. This is very important as this difference can impact the use of observed data in hydrological application, where it is important to know the exact amount of water fallen over the soil. At the same time, the approach used in state-of-the-art precipitation products, like for instance the one provided by GPM, is based on a top-down approach, providing an estimate of the instantaneous rainfall rate at the satellite overpass. This means that if we miss a storm, for instance, we can underestimate rainfall. In this study we carried out in 2017, we have seen that at least 10 passes per day are needed for obtaining a satisfactory performance in estimating rainfall. Soil moisture can help us in estimating rainfall as soil keeps track of the fallen water. In the same way in which we measure the water level in a gauge for estimating rainfall, we can estimating the water level into the soil using it as a natural rain gauge. This is the basic idea behind SSM-derived. It is based on the strong relationship between precipitation and soil moisture. In this graph, you can see the blue bars represent the precipitation, while the red dot the soil moisture values. You can see that after a rainfall event, soil moisture increase. So we can use this relationship to link the variation of soil moisture with rainfall. We use the soil water balance equation to describe the water fluxes within a soil layer. In this case, Z star is the soil water capacity, that is the soil depth times the porosity. I'm sorry. This term represents the relative soil moisture and its variation in time. P, R, E, and G represents the precipitation, the surface runoff, the evapotranspiration, and the drainage rate, respectively. During rainfall, surface runoff and evapotranspiration are assumed to be negligible, so we can estimating rainfall by using this very simple equation. It is based on the knowledge of the soil moisture and its variation in time between two different observations. Z star A and B are three parameters, that should be estimated through calibration. Of course, the quality of the rainfall estimates is related to the quality of the input soil moisture data. For instance, frozen soils, highly vegetated areas, compact topography, for instance, can impact the quality of the input satellite soil moisture product. So in this case, we can obtain rainfall with a lower quality. In this study we carried out in 2015, we have seen how we have estimated different contribution of the water fluxes related to the soil water balance equation, in which we can see that the contribution of the evapotranspiration and the surface runoff is very limited. So this is why we can neglect these two fluxes. We have applied the SSM-derived to several soil moisture products, satellite soil moisture products. In this case, you can see the application to the ESA CCI soil moisture product. In this way, we are obtaining a very long soil moisture derived rainfall data set. In this case, we have 18 years of rainfall estimates. And the data set is free available at Zenodo. So if you want, you can test yourself the data. Very recently, we have also applied the SSM-derived algorithm to the entire ASCAT soil moisture data record. In this way, we have obtained a very long, also in this case, soil moisture derived rainfall data set. Here you can see in this animation, you can see how the satellite soil moisture derived rainfall perform very well compared to the ERA 5 rainfall product on a global scale. And also in this case, the product is available at Zenodo. So the data set is characterized by a daily temporal resolution and a 12.5 spatial resolution, 12.5 kilometers, I'm sorry, of spatial resolution. So if you want, you can try by yourself. We have tested also the integration of several soil moisture data sets obtained through different satellite missions. In this case, we used ASCAT MAPAMS to rapid scat MOS soil moisture data set in order to obtain different derived rainfall products. But we tested also the beneficial effect of integrating all the estimates in India and in Italy. Here you can see the results. And where you see red, that means that the product is characterized by a high accuracy with compared to the ground observation. In this case, we can see that the merged product provides the best performance over the two different study areas. One of the last application is related to the integration of SSM-derived derived rainfall and a top-down approach, so a classical state-of-the-art rainfall product. In this case, we use GPM yearly run product to integrate the data with the rainfall estimate with the one obtained through SSM-derived. And here you can see from the correlation maps on the right, you can see how the integrated product provide very good results, even better than the one provided by the GPM final run product, that is the gauge corrected product. So in this way, we start to develop a new product within H SAF that is identified by H64. And in this case, we integrated the SSM-derived derived rainfall with passive microwave rainfall estimates over the MSG full disk area. The product is currently under development, but it will be released very soon. And here you can see the workflow and the input data we use to generating the H64 product. And basically, we use the soil moisture data obtained through Metop A and B ASCAT instrument, available as product H101 and H16 product using H SAF. We use the SWOT format at 12.5, and we regrade everything over the grid with spacing of 12.5 kilometers. And we integrate everything with the auxiliary module H23 that will be superseded by the H67 rainfall product. Regarding the workflow, first of all, we collect all the soil moisture data for in a temporal window of 24 hours over the study area, and we create a daily soil moisture map obtained by merging the information of the two different platforms. In this way, we can we can fill some gaps in the area between the different orbits of the satellites. And then we can compare these daily soil moisture maps with the soil saturation condition of the previous day we can apply SSM-derived we can obtain some soil moisture-derived rainfall over the study area. The SSM-derived parameters were calibrated through the use of H113 climate data record product using ERA 5 rainfall as benchmark by performing a long-term calibration during the period 2007-2017. Here you can see in this animation the soil moisture-derived rainfall over the study area. The white diamonds, let's say, between the satellites, the orbits are due, of course, to the absence of data in that area. So we are working also for integrating the Metop C soil moisture data in order to fill some gaps. Once the soil moisture-derived rainfall is estimating, we are reading everything over the H23 grid, that is a quarter-degree grid, and we integrated with these passive microwave rainfall estimates. Of course, the integration is performed only over land. I'm sorry for the typo. Just over land, because we can't estimate rainfall by using soil moisture over ocean. And if one of the two parent product is missing, we use only the other one. The integration is carried out by using this very simple NADI scheme, in which the weights are estimated by using by considering this equation that takes into account the Pearson correlation between the two datasets and the reference, in this case, ERA 5. And here you can see the spatial distribution of the integration weights, where you see higher value, let's say close to 1, we give more weight to SSM-derived. On the other hand, when you can see lower values, we give more weight to H23. And in this case, you can see how, for instance, at high latitude, where we have the presence of frozen soil, we give more weight to H23. The same, for instance, is valid over the Sahara Desert, where the soil moisture product is characterized by a lower quality. And at the end, we can obtain the H64 rainfall over the MSG full disk. And here you can see, for instance, that SSM-derived is able to capture this rainfall event, for instance, over France, here, or over over Sweden, for instance, while H23 is able to characterize the storm over the Sahara Desert that is completely missing over SSM-derived data. The product is characterized by a daily temporal resolution, 0.25 degrees spatial with a 0.25 degree of spatial resolution. Is an offline product, so basically it can provide rainfall with 1 day of latency, and it will be shared in NetCDF format. Here you can see the results of a first validation study we performed in 2017 over Italy against ground observation, in which we can see how the integration between passive microwave rainfall and SSM-derived rainfall can provide more reliable rainfall estimates, both in terms of correlation and root mean square error. The same, and here you can see the same similar study carried out over the MSG full disk, in which we can see the same results as I was explaining before. So basically, the integration can provide more reliable information over the study area. Here, compared with the GPCC, which is a dataset obtained through the use of ground observation, and against the ERA 5, that is our analysis dataset. we foreseen to apply SSM-Terrain to several soil moisture products in the next phase of the H SAF project. For instance, we are going to apply SSM-Terrain to the APS-SG sky instruments in order to obtain a very high resolution rainfall dataset. And as Giulia Panegrossi was saying yesterday, we are moving to the global coverage. We are going also to provide a gauge-adjusted integrated product in order to obtain even more reliable rainfall information. And we are going to provide also a data record, a rainfall data record obtained through the use of only soil moisture information on a global scale. This is the last part of my presentation, and I just want to show you a couple of applications of this data. Here you can see the results of a study we carried out over 600 basins throughout Europe. We use rainfall runoff model to simulate river discharge, and we test different satellite rainfall products as input, along with using an observed dataset as benchmark. And we can see that the soil moisture-derived rainfall and the integrated product between state-of-the-art rainfall product and soil moisture-derived estimates can provide very good results, very close to the one obtained by using the ground observation. But my colleague Christian Massari will talk about this on Thursday, so don't miss his presentation. Another application is related to the use of satellite rainfall data for landslide forecasting. And in this study, we carried out over Italy in 2018. We basically test different satellite rainfall products, along with, of course, in-situ observation, to test their capabilities to be used as providing useful information for landslide forecasting. And here we can see also in this case that the integrated product between a state-of-the-art satellite rainfall product and SSM-Terrain provide the best performance when compared to other satellite products. But also in this case, I will talk about this application next Friday. We are involved, and we were involved also in other applications related to the use of SSM-Terrain rainfall products. We use this data for instance, for crop modeling, for water resource management, and for validation of other satellite products, and for irrigation estimation. Sorry. So the use of SSM-Terrain can really expand to big field of interest. But if you want to, if you need further information about SSM-Terrain, you can just contact us, and we can provide you all the support to test the data for your applications. And thank you for your attention.